can set the pairing. So right now it sends every second, but we can set the encoding time.
Is it continuously sending, or is it waiting for a ping from the robot to start sending?
So how it works is this device first it sends a beacon message, then it listens for 15 milliseconds, and in that time, if robot sends that message and like send back a message, it continues to send, or they establish communication, so they can.
So beacons are for discovery, and then once it receives acknowledgement, then the transmission starts.
So if this device were laying on the forest floor, like you're saying, every 150 milliseconds, did it send out its beacon signal, or would you reverse that so that the searcher, the robot, would send out the beacon, and this would just be a listener until it needed to talk?
These devices actually receiving takes much more power than transmission, so it makes sense to send out a beacon and listen for as small a period as you can.
Okay.
And that is basically powered by something you can recharge more frequently, so we prefer to design it this way. But I think there have been studies that measure whichever design is better.
But one problem we're working on is to develop a protocol where, so the robot arrives at this node, downloads the data, and then gives an estimate of when it will arrive. So you have a distribution of the expected arrival of the robot. So the sensor can adaptively adjust its beaconing strategy. And of course, depending on the distribution, the right beaconing is not necessarily uniform. So that's kind of an interesting optimization problem there.
Does this have a certain amount of time to find the optimal location? Or?
So it changes with the, as I said, the environment.
Okay.
But during our experiment, it's let's say atmosphere.
If it's walking through a forest and it's surrounded by a very tight circle of trees, does it go up and to find the signal, or how does that?
So this design is actually a prototype for indoor environment. So this robot cannot work outside. But we just want to demonstrate that we can use this search algorithm to extend the life of modes. And also we have a bigger demo that we make this search, we download the data, then we go to another mode and do the same, download the data, and we bring all this data back to a gateway, and it continues in a loop. So this is the prototype that we developed here. So the only thing is probably the algorithm will be same, but depending on the conditions, of course we need to modify it. Also using these sensors, we will get more information. We can process that information to get better results.
So one thing is, I actually moved here last August. So I bought these little robots, and I guess I was naive enough to think that, okay, this will be enough. And then winter came and we decided, maybe we need some other robots for outdoor experiments. So that's why we started building this other one, which Pratap will actually explain. But the basic idea is, so those little robots, the laptop sends commands to them through some serial interface, and we kind of want to imitate it with these new robots. So basically we'll just develop the programs, run them on the laptop, and the underlying mobility platform will change, but we're hoping that we'll be able to port code from one platform to another relatively easily. So Pratap, why don't you tell us what you're developing? And
so, as said earlier, we wanted to move outside and we're going to use the iRobot Create. So what we have here, we just started developing this new platform. It's we're using the toy monster truck that comes. So this is a 1/10 scale exact replica of a monster truck. And so it's an exact replica up to the last nut. So So it imitates the features of what you would see normally in a monster truck. So this is basically the main requirement that we had, so that it is able to traverse outside in rocky terrains or in uneven surfaces. So we just started developing this. We want the basic functionality to be so what we have over here is we have 6 IR sensors, as you can see. So these 6 IR sensors are used to detect obstacles. So these work up to a range of 1.5 meters. So with the help of these 6 IR sensors, we'll be able to navigate. For obstacles that are smaller than this, this particular height, the robot is actually able to go over the obstacles. So you can see the shock absorber system, the suspension system that we have is pretty is good enough for it to go over low-lying obstacles. For higher obstacles, we have these 6 IR sensors. Again, similar to the iRobot platform, we have the laptop that will run the actual algorithms, and we'll be connecting the modes to this laptop. And the laptop is again interfaced with the lower circuitry that controls the low-level motion code and the interfaces with the different sensors. So this is the RF antenna. So you can control it with a remote control as you normally do in a RC truck. But for most of the time, we'll be using the onboard circuitry and the laptop on top to control the robot. And as time goes, we'll be adding more sensors. We're planning to add vision system for it to navigate off-roads. And so I actually had a wall following demo, but there's not much space here to do a wall following demo.
Why don't you just stand a couple people in its way and see how it moves around? Just a straight line, a couple people on the inside, see what doesn't run over their toe or something like that.
What we could do is, if we move outside later on, I'll just have it over there.
Yeah, okay. Can we move outside?
Sure, I guess this is the last demo. So
Yeah, I mean, we kind of move outside, maybe take it outside, and then there's some another kind of demo in the open area, so maybe people start moving it.